like I say, we're just going to work through, make sure that we know what's going on so that we feel comfortable for our trig. All right, so guys, generally your trig, you're going to get a question that, to start off with, will generally expect or require you to work with some sort of diagram on the Cartesian plane. This is very much a grade 10, grade 11 level question. And then we increase in complexity from there. So the first question, generally a basic, straightforward 10, 11 level question, and then we go from there. And I'll explain where we go from when we get there. So it says, it is given that root 13 sine x plus 3 is equal to 0, where x is an element of 90 to 270 degrees. Okay, so we just need to understand what this actually means. So firstly, when it tells us that x only falls between 90 and 270, if you think of your Cartesian plane, this whole first quadrant are all your acute angles. Then you get to your straight angle, your reflex angles, and then a full revolution all the way back around. And if x can only be from 90 to 270, essentially what that means is this whole first quadrant is out. Okay, x doesn't exist in that first quadrant. So now we've narrowed it down to 3 of our quadrants. And now we need to decide, based on this information we've been given here about our sine ratio, which quadrant we're actually working in on our Cartesian plane. Now, what's really, really important when we do start looking at these types of questions is we need to remember to isolate our trig ratio. Because in order for us to figure out what quadrant we're in, we need to be working with just sine x. Okay, so generally this will go in your working out for the first question. If not, just write down 5.1 and do your working out. You do get an answer book and paper too, and often the question will say without using a calculator and with the aid of a diagram. If it doesn't say with the aid of a diagram, I would still suggest you draw one because it is very helpful. All right, so if we take our, let's just do it here, root 13, it's a very aggressive pen, I do apologize, I'll fix it now. Root 13 sine x plus 3 equals 0. Our goal when we isolate the ratio is essentially to get sine x by itself. So that means we need to use inverse operations to isolate it. And so we will have root 13 sine x is equal to negative 3. And so sine x is equal to negative 3 over root 13. All right, so now that we know that the sine ratio is negative, we can go back to our diagram and we can figure out where we want to be. Now, this is where we need to remember cost. So cost diagram, I think it's probably more Western Cape thing, but some people learn it as all stations to Cape Town. I don't care how you remember it, just remember the cost diagram. So we need to figure out where sine is negative. Now, we've already eliminated quadrant 1. We can immediately eliminate quadrant 2 because sine is still positive there. And I've obviously just realized I had a brain fart earlier. This is up to 270, so we can actually eliminate quadrant 4 as well, which means that the only quadrant we have remaining is quadrant 3. And so that is where our diagram is going to be drawn. So once we've managed to narrow down our quadrants, once we've managed to narrow down where we're actually working, drawing a diagram is then our next step. It's very useful for us because we can then see very clearly what it is we're working with, particularly, and I mean, like, this is quite important, particularly the signs of the values in your ratio. Often we forget where x is positive and negative in our different quadrants, and that is very, very important when we're working with these questions. I don't know why I said theta, it's x. So there's our angle x, we're in quadrant 3, and so we can now go and have a look. So remember, your sine ratio on the Cartesian plane is, if you want to still work with opposite over hypotenuse, that's okay, but sine on your Cartesian plane is y over r, the y coordinate divided by your radius. Now, guys, if you have a look in quadrant 3, all your x values are negative, all of your y values are negative. So this negative must go with your y value. So if you wanted to imagine it as a triangle, this length over here is negative 3. Alternatively, your coordinate has a y value of negative 3 and some x coordinate or x value. Your r value is your radius is always positive. So this is root 13. And so now what we can see is we can use Pythagoras to go and work out the missing x coordinate or the missing x value. So this value for x. It is just a Pythagoras calculation. You do not need to show your substitution into Pythagoras. You don't need to show me any of the working out. You can quite literally go straight to your answer. And so x would be equal to 2 according to Pythag. But because it is on the negative x-axis, we are working with x is equal to negative 2. So this x value here and this x coordinate, negative 2. All right, now once you have all of this information, it means that you can work out the ratio of anything that you're asked for. So now we can go back to our original question, which is asked us for sine of 360 plus x. Now guys, don't let this trick you. 360 plus x, again, if you think of your Cartesian plane, is saying we've gone a full 360 degrees, and now we're going back into quadrant 1. So it's just an acute angle of sine. So sine of 360 plus x actually just simplifies to sine of x. And we already know that sine of x is equal to negative root 3, negative 3 over root 13, because that was what information was given to us. So don't let the 360 plus x trick you. It basically just means you're back in quadrant 1. You've done a full revolution. You're back in quadrant 1 now. Please also remember, it's asking you to do this without a calculator, hence why the diagram is so useful to you. Because once you know what ratio you're working with, i.e., for example, here sine of x, you quite literally just read that information off your diagram. There is nothing more that you need to do except for reading off the information. So when you get to something like 5.1.2, where I'm asking you for tan of x, you go to your diagram. So tan of x on your Cartesian plane is y over x, and you quite literally just go read those values off. The y coordinate was negative 3. The x coordinate was negative 2, and obviously a negative divided by a negative is a positive. This also makes sense. In quadrant 3, tan is positive. So it makes sense that we are getting a positive ratio here. So again, this diagram is so useful to you, because once you have that information, you're quite literally just reading stuff off. Okay, I'm just going to move this up because we don't need that much space. Right, the third one here says cos of 180 plus x. Remember, this is a reduction. We've seen this before. You have no idea what I'm talking about. Your reduction comes from your quadrants. This is all also in that info pack, but here we go. So the quadrant 1, 2, 3, and 4. Theta 180 minus theta, or 180 plus theta, 360 minus theta. So this 180 plus x is referring me to quadrant 3. Okay, 180 plus x, 180 plus theta, whatever you want to say, it doesn't really matter. We're now working in quadrant 3. That is helpful to me because I know in quadrant 3, cos is negative, and so this actually just reduces to a negative cos x. Once we know what it is, we can go and read off our information. So we know that cos x, and cos on your Cartesian plane is x over r, is negative. X was negative 2 over r, which was root 13. And so we get negative times a negative, which is positive 2 over root 13. All right, so again, don't let it panic you. All of these things, particularly in this first question, is grade 10, grade 11, reduction, simple ratios off your Cartesian plane. Excuse me. So that is 7 marks straight off the bat that we should be banking on. And again, use a diagram. Even if it doesn't say draw a diagram for yourself, because it will make your life a million times easier. It allows you to see what signs you're working with for x and y. R is always positive. And it allows you to immediately read off your values from your diagram for your ratios. Okay, so just a reminder, sine y over r on your Cartesian plane. Let's just do this. Obviously, you can still use opposite over hypotenuse and all of those things. So sine is y over r. tan y over x cos x over r. You can learn them like that. You can still use opposite adjacent hypotenuse. It really makes no difference. But when we do move onto the Cartesian plane, we are working with coordinates. So we do tend to work with x, y, and r. Okay, so first one, nice and easy, straight out the bat, nothing too tricky. I'm just going to stop here for you guys to take a screenshot, and then we're going to have a look at the next type of question that you get, which generally asks you to simplify an expression. Sometimes they say to one trigonometric ratio, and it involves you needing to work with your reduction formulae, your co-ratios. Okay, so like I said, we're just screenshotting, and then we'll have a look at this next one. So like I said, guys, generally speaking, it's not asking yet for any identities or anything like that in the second question, but it is expecting you to remember your reduction. And I've just written the reduction here in this last question in case we're not too sure. Remember, go-tolls, I mean, I didn't say it at the beginning of the lesson, but I think it's because we know the drill. If you have questions, just ask, okay? All right, so if we have a look at 5.2, this is your next type of question that you need to be able to deal with in trig. Simplifying an expression without a calculator. So very importantly, anytime you see without a calculator, it's going to mean one of two things. Either you're going to have to use your reduction formulae, like we are going to have to here, and your co-ratios, or if there's numbers involved, you're going to have to start thinking of special angles. All right, so in this case, because it is in terms of theta, we don't need to stress about special angles, but we do need to think about our reduction. Okay, so I'm just going to draw it again. Your reduction formulae, dependent on the quadrant you're working in on your Cartesian plane. Again, cast diagram, very important. And Greg tells us this is something that you easily forget or something that you're not comfortable with. This diagram I'm drawing right now, you draw it at the start of your exam. Doesn't matter where you draw it, scrap piece of paper, somewhere in the front of your booklet, whatever, you draw it so that you have it. Right, so these are all your reduction formulae. We also need to know our co-ratios. So the co-ratios are when you've got 90 plus or minus. So sine of 90 minus quadrant 1, so everything is positive, reduces or becomes cos of theta. Cos of 90 minus, again, still quadrant 1, so this becomes sine theta. Sine of 90 plus theta, we're now moving into quadrant 2. In quadrant 2, sine is positive, so this is just cos theta. However, when we get to cos of 90 plus theta, because we're in quadrant 2, cos is negative in quadrant 2. So this becomes negative sine theta. Everything else positive except for that cos 90 plus. Right, now that's important because as you can see, right in my numerator, straight off the bat, cos of 90 plus theta. So we need to use our reduction formulae and our co-ratios to go and answer this question. Now, guys, what's really important when you do these types of questions, I would try and go step by step as far as possible. So what I mean by that is don't try to simplify things in your head and get an answer. Write down the fact that cos of 90 plus theta becomes negative sine theta. Because what you'll see is that when you go through memos and past papers and stuff, you get a mark for every single reduction and co-ratio that you correctly simplify. So that's a negative sine theta. My negatives, sorry, I'm looking a bit strange, but it's okay. Sine of 180 minus theta. Now, what we need to be careful of is this looks familiar to us, but it's not quite identical. Theta minus 180 kind of looks like one of these two ratios, but it's usually 180 plus or minus theta. Now, what you need to remember is that, and it almost links back to this first, where were we? This first question over here of 360 plus x. You can add 360 degrees to anything, any angle, and you will end up in the same place. So what I mean by that is, if you're sitting, I don't know, over here at an angle of 120 degrees, if you add 360 degrees, you end up in exactly the same place. 360 degrees later, but you end up in the same place. If you had subtracted 360 degrees, you end up back in the same place. So when you get a situation like this where the order of your terms is incorrect, so it's theta minus 360 or theta minus 180, obviously plus doesn't matter because order of addition doesn't matter. But when it's a theta minus 180 or theta plus minus 360, just remember you can add 360 degrees. It's going to give you exactly the same solution. This is exactly the same ratio. So if we add 360, what that means is I now have sine of theta plus 180. And like I said, this is not perfect for us because order of addition doesn't matter. Whether you have got, I don't know what I'm doing, whether you have got 2 plus 3 or 3 plus 2, you're still going to get 5. So the order in which you add things doesn't matter. So now we can, in our next step, reduce this further to what we want. Right, when we then go to the second term in our denominator, that plus 3 times sine of negative theta, we now need to think of our negative angles. Okay, so there's actually a lot that we have been tested on here. Right, so negative angles. Negative angles are measured, usually we measure an angle from your positive x-axis counterclockwise. Negative angles are now measured from your positive x-axis clockwise. So what I mean by that is we would usually measure an angle up like that. This would be positive. But if we now go clockwise in the opposite direction, we are now working with a negative angle. Negative angles exist here in quadrant 4. And so according to our cos diagram, cos of a negative angle, because cos is positive in quadrant 4, just reduces to cos of theta. However, sine of a negative angle and tan of a negative angle, because these two ratios are negative in quadrant 4, this becomes negative sine theta and negative tan theta. So we are looking at this negative angle situation over here with the sine. And so in my denominator, this sine of the negative angle becomes negative sine theta. Right, and now we can start to simplify what we have. So obviously the negative sine theta in my numerator can stay there for now. Sine of theta plus 180, we're looking in quadrant 3. This is where sine is negative, so that reduces to negative sine theta. Positive 3 distributing to the negative sine theta becomes minus 3 sine theta. And now we've got some like terms in our denominator. So minus 1 sine theta minus 3 sine theta is negative 4 sine theta. And we still have that negative sine theta in our numerator. And now, guys, sine theta divided by sine theta, we can start cancelling. We can start simplifying here. Obviously, a negative divided by a negative is a positive. So these negatives essentially fall away. The sine thetas divide each other away to 1. And so what we're left with here is positive 1/4. And so this simplifies all the way down to 1/4. Just using your reduction formula, your co-ratios, and your negative angles, we have simplified it. 9 times out of 10, obviously not always, but 9 times out of 10 is going to simplify to a nice number, 1/4, 1, 2, whatever, or to a single trig ratio, sine theta, cos theta. That's it. Okay, so co-ratios, reduction formulae, negative angles. Very, very important to remember. Right, I'm just going to wait here in case you want to take screenshots, and obviously now I'm cold again. And again, if you have questions as we go along, please ask. Right, the next type of question, excuse me, that we get, sometimes it depends on how the exam set is feeling, will generally be a general solution question, or potentially they'll do the identity or proving the identity question first, but it'll be one of them. So in this paper, we had a general solution question first, and then we had the identity proof. All right, so general solution. Again, You either love it or you hate it, and there's lots of different ways to find the general solution. We have obviously done the method in our lessons using reference angles. Oh, excuse me. There are other ways to solve a trig equation with the general solution, and I don't mind how you do it. I use the reference angle mostly because there are steps that you can follow that will allow you to solve your equation every time. And for some people, it is just easier to follow steps than try and sort of problem solve it, guess what's happening. Okay, so just be mindful of the fact that there are different ways to solve a trig equation for your general solution. I'm going to use reference angles, and I think most teachers do use reference angles. All right, so we want to determine the general solution of the following equation. Cos x plus 2 sine x times 3 sine 2x minus 1 equals 0. Now, for whatever reason, your first instinct is always to go and distribute this. Guys, remember, so this is factorized. It's two brackets being multiplied together. If you have got a factorized expression equal to 0, you do not touch it. All right? You do not touch this equation. It is exactly what you want, because now we know all we do, according to a quadratic equation, is we take each of these factors and we make it equal to 0. So cos x plus 2 sine x equals 0, or 3 sine 2x minus 1 equals 0. One of these brackets must be 0 in order for my product to be 0. And so all we do is we make it equal to 0, and now we can go and solve these two separate equations. All right, so again, if it is already factorized and it's equal to 0, don't touch it. Make each factor equal to 0 and solve. All right, so I'm going to start with this equation here that I have on the left, the cos x plus 2 sine x equals 0, because many of us might want to go straight to a co-ratio. So we know that if we had cos of 90 minus, we could change that to a sine. Same as if we had sine of 90 minus, we could change that to a cos. But what I want you to remember is that you have an identity that tells you that if you have sine x divided by cos x, so sine of an angle divided by cos of that same angle, you get tan x. Okay, this is one of your identities that you learned in grade 11. And this is something that we need to use, or need to remember rather, when we are working with the general solution. So for this equation here on the left-hand side, I also don't know why I chose to put it so far away from our equation. Let's just move that over here. So if we have a look at this equation, that's exactly what I want to do. Now, how you choose to isolate this, I don't care, but we are going to have to divide by cos. So generally what I do is I leave the positive sine term, or I make the sine term positive. This will be equal to negative cos x. And now because I know my tan identity says I should divide by cos x, I'm going to divide both sides by cos x. So obviously that gets rid of it on the right-hand side. But on the left-hand side, this sine divided by cos x gives me 2 tan x. And a tan equation is lovely to solve, because general solution, we generally get two solutions for every ratio. Tan, you still are working with two solutions, but we can condense it into one. Again, you don't have to, but we can. All right, so first step of a trig equation, once it's nice like this with one trig ratio, is to isolate that trig ratio. So we want tan x alone, which means I'm going to divide both sides by 2, and so I've got negative 1/2 as my ratio. I now go and work out my reference angle. Now your reference angle, remember, is when you now type onto your calculator shift tan of 1/2. You ignore the sign. The sign we will use just now to decide which quadrant we're in. So we say shift tan 1/2, and we get our reference angle. So shift tan 1/2, it's not the nicest reference angle, gives us 26,56505. I think there's more decimals, but 5 is enough. And now we decide based on the sign which quadrant we're working in. Okay, so Here, tan is negative. If we think about, again, our beautiful little cast diagram, tan is only negative in quadrants 2 and 3. This is now where we decide what reduction we're going to use. Now, grade 12s, I said it earlier, but I'm going to say it again. For a tan equation, you only need to do one solution, okay? Because of the symmetry of where tan is positive and where it's negative, if you work out quadrant 2 solution and you add 180 degrees, you get quadrant 4 solution. If you add another 180, you go back to quadrant 1 solution, quadrant 2 solution, 360 degrees later. So there is no need to work out both solutions because of the symmetry of where tan is positive and negative. We just work with the plus k times 180. Okay, so I'm going to do just the quadrant 2 solution and combine everything. So what we now do is we take the angle we're trying to solve for, in this case it's just x, is equal to, and now we apply our reduction. In quadrant 2, it is 180 minus my reference angle, 26,56505, blah, blah, blah. And then we've got our plus k times 3, k times 180, because it's tan, k element integer. Right, we then just subtract that, 180 minus 26, whatever, 153,43 degrees plus k times 180. Again, grade 12s, if you want to work out both solutions, fine. You would then have plus k times 180. You would work out quadrant 2 solution and then quadrant 4 solution. But what this does by adding 180 degrees is it combines both solutions in one. Okay? But it is completely up to you. Right, so there's just a question of why do we divide by cos? So remember, we're dividing by cos because of the tan identity. So if you have a look up here in the corner, this little yellow block over here, the tan identity says to us that if we take sine x and we divide it by cos x, we're then working with tan. So we never want to work with two different ratios. So right now I've got a sine x and I've got a cos x. Those are two different ratios. I don't want two different ratios. So I divide by this cos x to make one tan ratio that I can now go and solve the equation for. Does that make sense? Okay, so can you just let me know if that makes sense? Okay. I'm not too sure what's getting you stuck. So I'm going to say it again. So just listen carefully. I'm going to say it again. If it still doesn't make sense, and we'll have to figure out another way to explain it. So in this equation over here, I've got a cos x and I've got a 2 sine x. These ratios are different. I do not want to work with different ratios. That is too complicated. We don't do that. We need to make it either a cos x or everything sine x or a tan. I need to make it one or the same ratios. Because these angles are both x, I can use my tan identity. If I take sine x and I divide it by cos x, that becomes tan x. And so rather than working with two different ratios, sine and cos, by dividing by cos x, I create a tan x, which is now one ratio that I work with. I never want to work with two ratios. So because our angles were both x, and because I had a sine and a cos, I manipulated my equation so that I could divide by cos x to create tan x, and then I can solve my equation. Okay, so again, let me know if that makes sense. It's just because we don't want to work with two different ratios. Awesome. Right, there's another question of please re-explain the negative sign by a half and the quadrant thing. Okay, so this is reference angles. If you solve trig equations differently, you do it the way you do it. However, when we use the reference angle method, so here, reference angle, what we do is we would say, let's maybe write it in, we ignore the sign. So to get this answer, on my calculator, I said shift tan, so tan -1, and I typed in a half. I ignore the sign. So I ignore the fact that it's -1/2. I just get my reference angle. I then use the sign to decide what quadrant I'm working in. So if we now go to this little diagram, I know there's a lot going on the diagram, but if I go over here, because I am working, yes. Okay, there's a lot going on. It's fine. So over here, because this is a negative, I want to go to where tan is negative. Tan is negative in quadrant 2 and in quadrant 4. So this is why I've applied the ratio 180 minus, because in quadrant 2, that is my reduction. I could have done the second solution of 360 minus, but because of this plus k times 180, when I add 180 degrees, as you can see here, from quadrant 2, I get to quadrant 4. So I'm automatically getting my next solution in any case. So reference angle, shift, sine, cos, tan, whatever, of just the ratio, ignore the sign, and then you use the sign to decide which quadrant you're working in. We're going to do, obviously, the sine one now in a second, so you'll see how we use that again. But the sign tells us the quadrant, the ratio gives us our reference angle that we work with. Right, Leila, does that make sense? Cool. All right, Kilebogile.
I wanted to ask that 2 tan x is equal to -1. You divided 2 by 2 both sides.
Good, exactly.
And then, ma'am, where there is 180 minus into 26, I don't know, 56. So that negative will determine the quadrant.
Exactly. So because I'm in quadrant 2, the reduction here is 180 minus whatever my reference angle is. So that's why I said 180 minus my reference angle.
So, ma'am, if it was positive, it will be plus.
Yes, exactly, because then it would be quadrant 3.
Okay, thank you.
Good. All right. Sorry, I saw there was one more question. If we took 2 sine x and used our cofunctions to make sine into cos, would we still be correct? Yes, you would still be correct. I would avoid co-ratios unless you're comfortable with them. The only time we ever really use co-ratios is if the angles are different. So if it had been like cos x plus sine 3x, for example, then we would use a co-ratio so that we can work with the same cos or sine or whatever. If your angles are the same, so like in this case here, they were both x's, I would immediately use tan. But like you say, it's not wrong to use the co-ratios. Personally, I avoid co-ratios and I don't use them unless I absolutely have to. But you will get marked correctly on that as long as you've used your co-ratios correctly. But like I say, I would avoid it. And unless you're comfortable with it, then by all means go for it. Okay, so guys, if we now go to the sine equation, because we have to solve both of them, we can't ignore it. We want to do exactly the same thing. So what we want to do first off is we want to go ahead and isolate our trig ratio. So I want to get sine of 2x alone. That is going to require me to add 1 to both sides. So I'll have 3 sine 2x is equal to positive 1. And then divide both sides by 3. So sine 2x is equal to a third. I have now isolated my trig ratio. Great tools, please understand that that 2 in front of the x is part of the angle. We cannot get rid of it. So you can't just now divide that by 2. That is nonsense. It is part of the angle. We need to deal with it when we start solving for the angle. So this is now where my reference angle comes in. So again, I ignore the fact that it's positive. Obviously, you're going to type it in as positive because that's what happens. But we will use the fact that there's a positive here now in a second to determine our quadrants. So our reference angle, we will type shift sine. So it'll be sine to -1 of positive a third. And that gives us a reference angle of 19,47122 degrees. Now we go and use that positive sign. So now I go and say, okay, the ratio for sine 2x is positive. According to my cast diagram, sine is positive in quadrants 1 and 2. So I only care about my solutions in quadrants 1 and 2. In quadrant 1, my reduction is just theta because it's an acute angle. And in quadrant 2, I've got 180 minus theta. So these are the 2 separate solutions I'm now going to have a look at. So I start with my quadrant 1 solution. You can start with quadrant 2 if you want. It's completely up to you. And our solution is going to be our angle that we're solving for. So 2x is equal to, because it's quadrant 1, it's just theta. So it's just the reference angle. Whoops. Plus k times 360. K is an integer. And now we go and solve for x. So we're going to divide everything by 2, inverse operations. Silly thing. Now, guys, remember, when you divide by 2, you divide every term by 2. So this divide by 2, this divide by 2, this divide by 2. This isn't a term. This is just like a restriction or a note that we make. Everything divided by 2. And so we get that x is equal to 19,47122 divided by 2 is 9,74. You can obviously round off now. Plus k times 180. And that is our first solution that we've gotten. Now, guys, think about this. It must become 180 because we know from trig functions, this 2x changes my period. Rather than getting one sine graph over 360 degrees, I now get 2 sine graphs over 360 degrees. My period of my graph has changed. So it makes sense that I now have plus k times 180. So that was quadrant 1 solution. We now have to go to quadrant 2 solution, and we do exactly the same thing and apply the appropriate reduction formula. So again, we take the angle we're solving for, 2x, is equal to, in quadrant 2, I'm now looking at 180 minus x, theta, or whatever you want to call it. So 180 minus your reference angle of 19,47122, plus our k times 360, etc., etc. We're solving. So how you choose to do this is up to you. 180 minus that 19, whatever is 160,528. And there's a whole long decimal, but we can just stop there. Plus k times 360. And again, we are going to divide everything by 2. And so we get x is equal to 80,26 plus k times 180. We divide everything by 2. And so these are our 2 solutions for the sine equation. And so according to my question of determine the general solution for this whole equation, your solutions are the solution to your tan equation and the 2 solutions to your sine equation. So we have a fair amount of solutions here. But always just remember, if it's already factorized and it's equal to 0, each one equal to 0, and you solve from there. Right, I know general solution is tricky. I know that we struggle with it. If you are still struggling with general solution, I would really recommend you go back and watch the videos from our lessons when we did general solution, because I do lay out step by step there what's happening. And I think I do it in the info pack as well that I put on Google Classroom. Obviously, I'm now. Yes, I've put step by step what you need to do there. So if it is something that you know you struggle with, please do go have a look at those past videos, at those past lessons, at just the information that I've given you, so that you can see exactly what you need to do. Right. Again, I know that it's no one's favorite. I do understand that. Once you get the hang of it, it does become a lot easier. And I know it feels like we probably always say that, but I promise you it does become easier. All right, yes, happy to show you the mark allocation. I do apologize. I will do my best to do that better. All right, so firstly is setting up both of these equations. So both of these equations you need to have set up. I'm just going to take that off because that's a lot. For this tan equation, getting to a point of tan x equals -1/2. For the sine equation, getting to the point of sine 2x equals 1/3. You then get a mark for your first solution here for your tan equation. So that's 4 of our 6 marks. You get a mark for your 9,74 plus k times 180. and you get a mark for your second solution for sine 80,26. Okay, so if you think about it, half of your marks are just by isolating your trig ratio before you even start solving. The solution is the other 50% of your marks. So even if you forget about the general solution, quadrants, reduction, whatever, you can still get marks for just isolating your ratios. Okay, so that is really, really important. That's literally the first step that I've said that we need to do when solving a general solution. No problem. Leila, I'm sorry. I will be better. In my head, I do it, but then I don't do it, obviously. All right, so I'm just going to stop there for you guys to take a screenshot, and then we'll have a look at the next type of question, which is proving an identity. A lot of things happen in my head that then don't make it out into the real world. I once had a conversation in my head with a matric class I was teaching about the fact that their test date had moved a bit later. And I saw them in class a few days later. And I was saying, oh, guys, the test's on this date. And they all just looked at me and they were like, what are you talking about? I was like, no. And I lost a little bit. I was like, don't be ridiculous. This, so typical. You never listen. And they're like, ma'am, I promise you never told us. And then I realized I'd had the whole conversation in my head and had not actually conveyed that information to anyone. And so did have to apologize profusely. And then we had the conversation in real life. Yes, it is something that happens a little bit too often for my liking. Okay, so moral of the story, if you think I should be doing something that I haven't done, just ask. I'm probably doing it in my head and just not doing it out loud. Okay. All right, so guys, the next type of question that we need to be comfortable with is an identity question. All right, so in my infinite wisdom, I wanted to put this here for us so that we could see our, why do you hate me? Technology. Okay, I'm not going to fight with it because that will just end me for today. So I'm just going to roll with it. Right. Just very quickly in terms of identities. Firstly, all of the identities in the red rectangle are on your formula sheet. The only ones that are not on your formula sheet are the ones that you learned in grade 10 and grade 11. So the tan identity, so the one that we literally just used to solve our equation, as well as the square identity. So the square identity is the fact that sine squared alpha plus cos squared alpha is equal to 1. And we need to know the manipulations of this. So manipulations being that cos squared alpha is equal to 1 minus sine squared alpha. And sine squared alpha is equal to 1 minus cos squared alpha. So these are the only ones that are not on your formula sheet. You need to know those. And they do come up, so please learn them. All right, again, even if it's a case of the second you start writing, you quickly jot them down for yourself, it's there. Right, so we have been given the identity cos of x plus y times cos of x minus y is equal to 1 minus sine squared x minus sine squared y. And the first question is asking me to prove the identity. Now remember, when we are proving an identity, we work with one side. You either choose the left-hand side or you choose the right-hand side. That's it. You cannot work with this as an equation. You pick a side. Now, oftentimes you can work with both sides. Like you could pick either one and you'd be fine. But my advice is if you really don't know, go to your identities. So yes, you could change sine squared x to 1 minus cos squared x. And yes, you could change this to 1 minus cos squared y. And yes, you could change the 1 to sine squared alpha or sine squared x plus cos squared x. Absolutely. And to be honest, I haven't tried it. It might very well work. But look out for identities that you can immediately identify for yourself. So what I mean by that is this cos of x plus y is a compound angle formula, cos of alpha plus beta. I can go and write or expand that, and I can go and get a solution. Same as this cos of x minus y is a compound angle formula or identity. I can go and expand that to get multiple terms. Again, I'm not sure if it would work with the squares. It probably would. It might not be particularly nice to work with, but it might. Well, I'd have to go and try it by myself and see. I don't want to waste your time. But oftentimes, if there's a compound angle or double angle, use the identities. So I'm going to work with the left-hand side. Indicate for your marker which side you're working with, so left-hand side. And now we're going to expand both of those things. So the first expansion is this cos of x plus y. Literally just use your identity and expand it. So it's cos of x times cos of y minus sine of x times sine of y. And we're just going to chuck that into a bracket because we now need to multiply it by the next identity. The next identity is the cos x minus y. So this expands to cos of x times cos of y plus sine of x sine of y. So the cos identity is cos, sine, and then it's the opposite sign. So this was cos of x plus y. So the sign there is minus, x minus y. The sign we use is plus. How you choose to remember it is up to you. You also don't have to remember it because it's on your formula sheet. Right, once you have decided what identity you're using and you've substituted and you've done that expansion, manipulation, whatever you need to do, all you are doing from this point, guys, is algebra. You might have to factorize at a point. You might have to distribute at a point, add some like terms, but it is quite literally just algebra. If the cos x, y, and all that stuff confuses you, change them to variables. Okay, I wouldn't recommend it because you need to then change them back. But if it really does confuse you, make cos x represent A. Make cos y be represented by B and go from there. Just remember to change it back. All right, so we essentially now have a binomial times a binomial. Here's term 1, term 2, term 1, term 2. We have a binomial times a binomial. Now, guys, if I had given you, let's say, x minus 4, x plus 4, and you had to multiply that out, what do you know that's going to simplify to? Think back to your algebra, your factorization. What do you know this simplifies to? Oh, have we forgotten our algebra tools? What are those two brackets? Factorization. Thank you, Leila. This is the difference of square, guys. When you have identical brackets, one with a plus, one with a minus, you end up with a difference of squares. Okay, so what that means is if we look at what we have, we've got a cos x cos y minus sine x sine y, and then a cos x cos y plus sine x sine y. So what we actually have here is two brackets that represent the difference of squares. Now, the reason I'm pointing this out is because we know that when we go and distribute, okay, these middle and outer terms are going to cancel each other out. You would have a minus sine x sine y cos x cos y, oh gosh, and then a plus sine x. I'm not writing that all out because there's a reason that it becomes difference of squares. They cancel out. So we don't have to go and try and do anything super fancy. We quite literally take the first term multiplied by the first term, cos squared x, cos squared y, minus, because it's a difference of squares, multiply the last two terms, sine squared x times sine squared y. That is it. All right. So when you can identify these things, difference of squares, trinomials, etc., it does make your life easier. Right? Am I still cutting? Is anyone else struggling? No? You are struggling? You're not struggling? Okay, great. All right, so guys, at this point, and again, this would be for anything. If you now are stuck in terms of where you need to go, all you do is you go back and you look at the side you're trying to prove it's equal to. If I look at my right-hand side, I only have sine terms there. I've got no causes. So what that means is this first term I have a bit of an issue with. I don't want those causes there. I also see that I have a 1. So I somehow need to change these cos squared x and cos squared y to be only sines and introduce a 1 somewhere. And this is where your knowledge of identities comes in. Cos squared of an angle can be written as 1 minus sine squared of the same angle. And so what we can do is that for this first cos squared x, we can now expand this, or we can use our identity to write this as 1 minus sine squared x. And for the second cos squared y situation, we can now write this as 1 minus sine squared y. And then we still have our minus sine squared x times sine squared y. Again, great tools, all algebra. Okay, everything I'm doing right now is just algebra. I'm applying identities, but in terms of my simplification, algebra. So once again, I've got a binomial times a binomial here, so I'm going to have to expand that. 1 times 1 is 1. 1 times negative sine squared y is minus sine squared y. Minus sine squared x times 1 is minus sine squared x. And just making sure I haven't completely lost my mind. No, okay. And then minus sine squared x times minus sine squared y becomes plus sine squared x times sine squared y. And then we still have this last term, minus sine squared x times sine squared y. And hopefully what you see is that these last two terms actually cancel each other out. If you have a positive sine squared x sine squared y and a minus sine squared x sine squared y, becomes 0. And so what we are now left with is 1 minus, and remember we want to write it as the right-hand side. Doesn't matter if you reorder terms as long as you keep the signs correct. Minus sine squared x minus sine squared y. And we have proven, panic, that our left-hand side is equal to our right-hand side. And that is the whole goal of an identity. You want to prove that your left is equal to the right. You will only manipulate one side, and you want it to get to look like the other. And that's why I say to you, if you're feeling stuck, always go back to what side you're trying to prove is equal. Look and see, okay, well, if there's only signs, I need to get rid of the causes. If there is a tan, it means I need to use my tan identity, etc., etc. Use it as your guide to figure out what it is that you need to do. So guys, again, aside from the identities, this was all algebra. It was distributing and it was adding and subtracting like terms. That's it. And that you've been doing since grade 8. So when you get identity questions, just think to yourself, I'm just working with algebraic methods, distribution, factorization, like terms, etc. That's all you're doing when you're proving an identity. So don't overthink it. Don't panic. It is just algebra. Okay, so I'm going to stop here in case you want to screenshot this. Obviously, again, if you have questions, just ask. And like I say, use your formula sheet, use your identities, identify what you can replace, what you can expand, etc. Right now, often leading on from an identity question, there will be two types of lead-ons. So this is 5.4.1. Option number 1 from a lead-on is if your identity contains a fraction, it will ask, where is this identity valid, or where is this identity undefined? Remember, a value, or specifically a fraction, is only undefined when its denominator is equal to 0. So I'm going to give a very, very basic example here. But let's say you had an identity of sine x over cos x equals tan x. We know this identity is true. If I now asked you, where is this undefined? You know that it would be where this denominator is equal to 0. And so now you've got an equation you can go and solve for x. Normal trig equation, easy peasy. Another thing that we need to take into account when we're looking at undefined is the fact that tan x can be written as a fraction of sine x over cos x. So anytime you have a tan x, you would also need to take into account what happens with that denominator. And so again, set up your equation. In this case, it would be the same thing, so you won't have to worry. But that's option 1. Where is your identity undefined or invalid? Something like that. Option 2 is where we use that hence situation. I say hence. When we use a hence situation and then give you numerical values. So it says, hence determine the value of 1 minus sine squared 45 minus sine squared 15 without using a calculator. Now, we might panic because those are not special angles. So we're like, what on this planet are we doing? We don't need to panic. Do you see that this expression that they've given us here is essentially this exact right-hand side of my identity? They're the same thing, except instead of x and y, I now have 45 and 15. That's it. And so what we need to remember is the second it says hence, it's saying you already know something about this expression. And what we already know is that 1 minus sine squared x minus sine squared y is the same thing as cos x plus y times cos x minus y. And so all we're going to do is we're going to substitute in. So we know that cos x plus y times cos x minus y is the same thing as 1 minus sine squared x minus sine squared y. This 45 degrees is x according to our expression. This 15 degrees is y according to our expression. So all we do is substitute in. Again, don't overthink it. Just sub it in. So we have got cos of x, 45, plus y, so plus 15, times cos of x, 45, minus y, so minus 15. Cos of 45 plus 15 is cos 60. And as said, without a calculator, so special angles, definitely going to be used, times cos of 45 minus 15 is 30. Now, great Halls, if you forget your special angle triangles, I don't want to say who cares because that's not fair, but use a calculator. It's not the end of the world. However, your special angle triangles, just in case we would like to know what they are. Oops. And yes, 45 degrees is a special angle, but obviously you're adding and subtracting, so we would work with what we have. So 30, that's a terrible 30. 60. I'll draw the other one now, but this is the one that we're going to use. So this is our 60-30 triangle, the 45 triangle, a little bit easier to remember. Some of you might have learned the 45-degree triangle a little bit differently, but this is how I work with it to ensure that I always end up with rational ratios. Root 2, root 2, 2. Some of you might have learned it as 1, 1, and then your hypotenuse root 2. It really doesn't matter. Okay, absolutely no difference. Right, so those are your two special angle triangles, which means that we now use them to go and answer this question. So this first ratio is cos of 60. So here's 60. Cos is adjacent over hypotenuse. So cos of 60 is a half. Then we want cos of 30. So we're now going the other side. Here's the 30 degree, adjacent, hypotenuse. This was root 3 over 2. You now go and multiply those two things together. 1 times root 3 is root 3. 2 times 2 is 4. Root 3 over 4. Done. Again, don't overthink it. The second you see hence or otherwise or something like that, use what you already know to answer the question. All right, I'm just going to do this in case you didn't get the screenshot initially. Let's take screenshots of that. And then we'll have a look at our next type of question, which generally, I don't want to say is a problem-solving question, but generally is going to involve some sort of metric level, either the compound angle or the double angle identity. We've already used the compound angle, so it's probably going to be a double angle, but testing a sort of higher level. Okay. All right, so we have been given the trigonometric, sorry, Lorato?
Hi, ma'am. Do you mind zooming out a little bit? Because the last time I couldn't get a full and clear picture.
Is that better?
Yes, ma'am.
Okay. Just let me know when you're sorted.
Thank you, ma'am. I'm fine.
Cool. All right, so what we have here is consider the trigonometric ratio 16 sine x times cos cubed x minus 8 sine x cos x. We want to do a few things, but the first question asks me, rewrite the expression as a single trigonometric ratio. Now, again, we might look at this and think, no, thank you. It was nice of you to offer, but no thanks. However, start to identify things that you can kind of make links with. So what I mean by that is this sine x cos x situation. Granted, it's a cos cubed x. We can get there. That should automatically remind you of the sine double angle identity because it's a sine cos. Yes, there's a 2 coefficient there, and we can sort that out if we need to, but immediately we need to be making those links. All right, so when in doubt, and particularly when there's something common in both of your terms, factorize. So what I'm going to do is, maybe let's just write this down, is I'm going to factorize this expression by taking out a common factor. Can anyone tell me what my common factor here would be? What is the common factor between these two terms? I don't know. Sounded like someone had an answer. Nice, Lorato. Okay. So 8 sine x cos x. Beautiful. So we take that out. That leaves me with 2 cos squared x minus 1. Now again, this should be familiar to us. If we go and have a look at our formula sheet and specifically our trig stuff, 2 cos squared x minus 1 is a cos double angle formula. Lovely. So this is going to simplify to, let's get this right, 8 sine x cos x times, I'm just going to keep it in brackets for now, cos of the double angle, so 2x. We're not really getting anywhere closer. All I've managed to do is get rid of a sine. I still need to get it to a single trig ratio. All right, so let's see what we can do. Again, we should be taking note of the fact that this is reminding me of my sine double angle. Now we know, and this is, I think, where sometimes we get a bit stuck. We know that we need to have, in order for our sine double angle to apply, 2 sine x cos x. That will give me a sine double angle. Now, if we think about this logically, I have got a coefficient of 8. So all that means is I would need to have a coefficient 4 because 4 times 2 is 8. Then I have my sine double angle that I want. So always just remember that coefficient, if it isn't 2, break it up into its factors so that you have a coefficient of 2. So what this now will simplify to in my bracket here is a sine double angle. So I will have 4 of sine 2x times cos 2x. So now we're getting somewhere. Now at least I've got a sine and a cos. We're getting somewhere. It's happening slowly but surely, but that's okay. I want one single trig ratio. Now again, the fact that I have a sine x times a cos x should take me back to my sine double angle. Again, I would like to write this as 2. Sometimes I wonder what my brain does. 2 sine 2x cos 2x, because that is my double angle identity, but my coefficient is 4. So all that means is I would have 2 times that situation. And what is now going to happen is this whole double angle identity simplifies to sine of the double angle 4x. This is now a single trigonometric ratio. And then I still have my coefficient 2 here. All right, so this is a bit nasty because of the number of times we had to use double angles. But when you are starting to see sine and cos of the same angle, whether it's 2x, 3x, 7x, if they are the same angle and it's a sine times a cos, you can apply your sine double angle identity. And we could keep doing that until we could simplify to a single sine double angle. All right, so again, look out for things that are familiar. Look out for your double angles. You have a formula sheet with you in your exam, so have it next to you, rip it off the pack, whatever you need to do, but have it next to you and start identifying these things that look like the identities that you can use and now apply here. Lorato?
Ma'am, do you mind you explaining from the 4th step, just after we separated the two?
This step over here?
Yes, ma'am.
Okay, so you understand how I got 4 times 2 sine x cos x times 2 cos x?
Ma'am, do you mind re-explaining again?
Okay. So we can see that the sine x cos x looks like my double angle. So let's just write this out here. Sine of 2x is equal to 2 sine x cos x. So this little pink rectangle that I have here matches up perfectly to this part of my identity. However, what I am missing is this coefficient of 2. But that's okay because I've got a coefficient of 8. If I split 8 up into a factor of 2 times something, that would be 2 times 4. So I can put my coefficient of 2 that I need with my sine x times cos x to get my sine double angle. So this will become sine 2x, which it does. I then still have that coefficient of 4 because 4 times 2 gives me 8. I can't just ignore it. But I'm able to manipulate that 8 and write it in a slightly different format. So once I've got my 2 there that I want, I can simplify this to sine of 2x. And again, what I now need to realize is that because I've got sine of 2x and cos of 2x, this once again looks like my identity. I'm just missing the 2. I still have a coefficient of 4, so I can break 4 up to be 2 times 2. And this is what I have over here. I can introduce my coefficient of 2, and this becomes my double angle, and my coefficient of 2 still remains there. So I think this is where it gets confusing / tricky. Just remember that if you have a coefficient that isn't 2, you can make it 2. So even if you had something like like, let's say it was something really ugly, like 7x cos x, okay? If you have 7 over 2 times 2, that gives you this coefficient of 7. So you could break this up into 7 over 2 times 2 sine x cos x, and then you have your double angle, 7 over 2 sine of 2x. So even if your coefficient is not a multiple of 2, you can still do it. You can break it up into factors that involve a 2 so that you can create for yourself the double angle identity that you want. Usually we're not that ugly. Usually it is a multiple of 2 and it's relatively easy to go from there. But you can do it with anything. All right, so even if it was like, I mean, now I'm just making up examples, but you can do it with anything. Okay, so Lorato, does that make a bit more sense?
Yes, it does. Thank you, ma'am.
Cool. This is one that they do tend to ask a fair amount. So if you go through a few past papers, you'll probably find another question like this. I know I've seen another one, but obviously I can't remember which year it was now. It'll hopefully come to me at some point. All right, so guys, I really like this next question, and it sucks that it's only for 1 mark, but I also understand why it's only for 1 mark, because it's also something that we would panic with. So it says, for which value of x in the interval x is an element of 0 to 90 will this beautiful thing that we've just worked with have its minimum? So again, we panic because we think, well, what on earth is that? As a graph, what is that? Remember, you have just shown that this 16 sine x cos cubed x minus 8 sine x cos x is exactly the same thing as 2 sine 4x. Exactly the same thing. Now, label, okay. Sorry, guys, let me just go back. So the question is, how did we get the 4x in the answer? So this 4x, remember it's a double angle. So it's double the angle that we have here. So 2x times 2, 4x. I often sometimes struggle with that. But it is the double angle reduction, so we double the angle. Does that make sense, Lebo? No, don't stress. Like my brain struggles with it as well, because there's 2s and 4s and 8s, and then I must double angles, as long as it makes sense. When I did the first time, I forgot. So it's absolutely fine. All right. So again, in this next question, we already know that the 16 sine x blah, 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 blah is the same thing as 2 sine 4x. We can imagine this. So this should be taking you back to a graph situation. We can imagine this as a graph. All right. So f of x equals 2 sine 4x. We know what all of these things do. The 2 in front of my sine is the amplitude. The 4 in front of the x affects my period. Okay, so this 4 is telling me that everything is happening 4 times quicker. Now, we know if we wanted to work out the period of a graph, we would take the normal period, 360, and divide that by 4. So the new period would be 90 degrees. Look at that. We're working in the first period's interval. Okay, now, if you think about a normal sine graph, this is your sine graph. Beautiful, beautiful. It has a maximum at 91, an x-intercept at 180, 0, and 360, 0, and a minimum at 270, -1. It's asking us for the minimum value. So the point that we're concerned with here is this point over here, this minimum value. But we'll get there. So let's establish what each of these things sort of do. This 2 in front of my sine, this is going to increase my amplitude. Oh, that's a bit embarrassing, but it's all right. To now be at 90 positive 2 and 270 negative 2. And the period is telling me everything happens 4 times earlier. So what that means is, instead of this maxima being at 90, it now needs to be 4 times earlier at 22.5. Instead of my x-intercept being at 180, it needs to happen 4 times earlier at 45 degrees. Instead of this minimum being at 270, it happens 4 times earlier. And if you don't know how to do that, just divide this by 4. 270 divided by 4 is 67.5 degrees. And that is the x value where we will have the minimum for this graph. So this should be taking you back to your trig functions. Yes, it is not a trig functions question. I'm not asking you to draw a function or anything like that. But the second you see minimum value in an interval, something like that, you need to go back to your trig functions and understand what these manipulations are doing to your graph. If you need to sketch it out, do it. I'll be honest, I need to sketch it out. I need to see what's happening. That's absolutely fine. If you can visualize this all in your head, well done you, you're better than me. That's also absolutely fine. But visualize what a sine graph looks like, visualize where that minimum would exist, and take into account the manipulations that have occurred. All right, any questions? Good. Okay, we've got 8 minutes. I'm trying to see which one I want to do. Okay, let's do this one. Right, so this next one is from November 2019, but I'm going to skip to this question over here, 5.2. Just because it's one that relies solely on co-ratios. And again, I know that co-ratios aren't necessarily always our favorite thing in the world. All right, so it says, without using a calculator, determine the value of sine squared 35 minus cos squared 35 divided by 4 sine 10 cos 10. Now, immediately, without using a calculator, and because I've got actual numerical angles, I need to be thinking of my special angles. However, the problem is none of those are special angles. None of them. So now we have to think, okay, eek. If I can't make them special angles, which I can't really, like I can't say 45 minus 30 or anything like that to get 35 or 10, I need to now think, is there a way for me to get a co-ratio? All right, now again, look at what you've been given and try and see what matches up with identities that you know. So this denominator over here, immediately, it's fresh in our minds, needs to go to a sine double angle immediately. If you don't get there immediately, that's absolutely fine, but just start training your eye to see these patterns. The next thing that we should notice is, although not identical, we can make it identical. This sine squared 35 minus cos squared 35, this matches up with one of my cos double angle identities. The terms are swapped, which is a problem when we subtract, but we can fix that easily. Okay, now the reason why I'm starting to think about this sort of stuff is, if I've got that cos double angle in the numerator, when I eventually simplify it down to the double angle, double 35 is 70, okay? In my denominator, when I eventually simplify that sine double angle situation, double 10 is 20. 70 and 20 are co-ratios. A co-ratio, the angles must add up to 90. 70 plus 20, 90. So immediately I'm starting to think 3 steps ahead of where I am so that I know I'm on the right track. Okay, so first things first, this order in my numerator is incorrect. I need to fix that. To change the order, just take out a negative. So take out a negative as a common factor. We now swap the order, cos squared 35 minus sine squared 35. This is now my cos double angle, which is great. And in my denominator, we're going to do exactly what we did in this last question. I don't want a coefficient of 4. I want a coefficient of 2. So I need 2 sine 10 cos 10. But obviously my coefficient was 4. So that means I should times by 2. 2 times 2, 4. Now I can get my double angles going. So in my numerator, cos squared 35 minus sine squared 35, cos double angle. So this simplifies to a negative cos squared 75 degrees. Remember, it's still squared. We can't just ignore the squared. Also, it doesn't because I'm just, losing my mind. The squared falls away because it's a cos double angle. So 35 times 35, 70. I think I also wrote down 75, so I'm doing real well here. In my denominator, the coefficient 2 stays there because that's not part of my identity, but the 2 sine 10 cos 10 simplifies to sine of the double angle, 20. And this is now where the co-ratios exist. 7 and 20 give me the 90. Now, grade 12s, you can decide which one you want to change. If you want to change the cos 70 or the sine 20, that's up to you. Okay, completely up to you, your choice, your life, you do you. Personally, I mean, it honestly makes no difference. I would probably leave the negative because I know that I'll probably confuse myself with too many signs. So I'm just going to leave cos 70 as it is, and I'm going to change the sine 20. Now, when you change the sine 20, you just need to be very careful. we need to rewrite this so that whatever expression I put in my angle does still represent or does still give me an angle of 20. So this would be 90 minus 70, because 90 minus 70 does give me the sine 20. But now this allows me to apply the co-ratio. So this sine of 90 minus becomes 2 cos of our angle 70. In our numerator, we've got negative cos 70. And so now we are able to simplify by saying cos 70 divides by cos 70, leaving me with negative 1 over 2, or negative a half. Okay, so what you're going to start to see as you go through more and more past papers, excuse me, is identifying your double angles and compound angles and stuff is going to be very, very important. Even if it doesn't look like what you need it to look like, trig is all about manipulation. Okay, 80% of trig is just manipulating your expression until you get it to be what you want it to be. This is all manipulation. Yes, I used some double angle identities, but once I was done with my double angles, I manipulated it until I got what I wanted. Okay, so co-ratio is super important. It never matters which ratio you choose to swap. If you had done the cos, it would have been fine. So this would have been minus cos 90 minus 20 over 2 sine 20. Cos 90 minus just becomes minus sine 20 over 2 sine 20. The sine 20s cancel, and so you still end up with negative a half. So it really makes no difference, but I know who I am as a person. This whole situation with a negative will confuse me. So I wouldn't do that. If you're comfortable with that, go for it. Okay, whatever you want. It's up to you. But co-ratio is very, very important. All right, I'm just going to wait here in case you want a screenshot. Right, it is 15 seconds until 7 o'clock. So if you need to go, that's absolutely fine. I do understand you might still have studying that you need to do. There's a question, Lorato.
Ma'am, please can you scroll up to the question we did before this one?
Okay, cool. I'm just going to wait 2 more seconds in case anyone's still screenshotting, and then I'm going to scroll up.
Okay, thank you, ma'am.
Okay. There we go. It's like a unicorn vomited on our screen. There's so many colors. All right, guys. But for those, I nearly said it came out the other end, but I thought that probably wasn't appropriate. I mean, I don't think vomiting is appropriate either, but whatever. Anyways. Okay, sweet children, I hope that you have a lovely rest of your evening. I hope that whatever you're writing tomorrow goes well. And I will see you on Wednesday, where we're going to look at trig functions as well as 2 and 3D trig, our favorite. Okay, I hope you have an awesome evening, guys. Rest, don't work too hard, and I'll see you on Wednesday.